Okay, so hoping a few more people will drop in, but if they do, you'll have to pass on to them that what we're going to do for just a few minutes is this entertaining historical note. We were talking about the property of logs, that the log of A plus the log of B equals the log of A to B. Mathematically important, but used to be, well, it still is, computationally important. Before we had cheap calculators that everyone had, you sometimes had to multiply numbers. This is a table, a special table of logarithms from a book. There were probably about 20 pages. This is 5 place. I'll show you what that means. Let's say I wanted to multiply a number, say 101.32 and 105.75. And I didn't have a calculator. I could do that by hand, but it would take a little while. Maybe I have some other numbers to multiply too. It gets more complicated. But let's see how we used to do it using logs. If you look down the left side, you can see that I can look up first number, 101, and then I have to look across to 3, and I can see the number is 00561. And I also need, since this is log to the base 10, I can manually figure out the integer part by where the decimal is. That's 2. Now, what about the 2 here? Well, that's between the 3 and the 4, right? It's 3, 2. So I look at these two numbers here and I do something called interpolation. I say, well, wait a minute. From 561 to 604, what is it? That's 39 plus 3 is 42. And then to help me out, they have a little table here called proportional parts. It tells me, since under 42, I can look up and see that 2 is 8.4, so I have to add 8.4 here. I don't really need the 4. I'm not trying to be that accurate. And then I can do the same thing for this number, 105.75. There's the 7. And I don't need that little table. I can see from 7 to 9 is 42, so I'm just going to add 21. So that's 02407, 02407, and I have to add 21 to it. That's only if I want to get that 5th digit to be accurate. Okay, so what do? I have the log of A and the log of B. I'm going to add them. All right, that's, in this case, not too hard. 7, 9, 9, 2, 0.4. The 4 here just tells me my exponent. This is going to be a number between 1 and 10 times 10 to the 4th. Now, what do I do with this? This is again, this is the log of A times B, so I have to look this up in my table. So 02997, let's look in the table. 029, where is that? There it is. That's 1071. 1071. And now, again, I can do this interpolation here. 79 to 19 is how many? That's 21, 40. So I look at my little 40 table, and now I have to, do two things at once. 979, 979. Difference is 16. So I look up in my little 40 table. But I just not off here. Screen. I look up 16 and I see that's 4. That tells me my last digit is 4. So times 10 to the 4th, or if you like, 1071. That's my answer. So, kind of tedious, and you got to sit there with this book. You got to lead through the pages. But again, consider you don't have a calculator. Just adding numbers is a lot easier than multiplying them. There's some operations that would be really hard to do otherwise. Like, I want to find the square root. Well, I can look up the log. Now I divide that in half, and now I've reversed my log table and I've found the square root. So this is more or less how it was done. Even computers, like before the 50s, there weren't even computers for scientists to use. There's a neat device, though. I don't know if it's still there. In the Computing Museum in Santa Clara. It's called somebody built this. Somebody designed it like 200 years ago, 300 years ago, and then they built one. Just pumped out tables like this, very accurately. Okay. That was for your entertainment if you came late. It won't be on the exam. Although it would be fun, but on the exam. Don't have my keys. That's so bad. I don't feel like I can do anything. All my keys are missing. So I'm going to spend a minute here.
Create a bigger debt.
They're either here or they're in the next room. So I will be back in just a second.
Wait, my mom texted me and was like, how much you need to pay off your credit card? And I was just like, there's no way I can tell her the truth. I would like 1,000.
Just don't spend it. It's already 1,000 monthly. 2,000.
Nah, I think after next month it'll be fine.
So they're not next door either.
With like development people?
Yeah. I have one project that started last week, so like it'll be like 2 months and I should be fine.
I have my cousin that wants to work on it too.
My apologies, I will catch up in just a minute.
Okay.
So.
We'll just talk after this.
You really can't show that Mac?
Yeah.
Really?
I'll see. I'll check. My roommate's selling one too though. It's a 15-inch.
15-inch, what year?
I don't know, I'll ask him. I think like
All right.
2 years old or something.
Yeah, the only thing is I don't want to get hustled. I don't know anything about Macs. Never used them. I never.
I'll check.
Okay, I want to go back to where we left off with logs. Just want to do something to warm you up a little bit. Let's look at this problem here. What I want to do here is I want to expand this. So I only end up with expressions of the form log of x. So some combination here of things like log of x. How would I do that? How would I use the laws of logs that we went over on Wednesday? Any ideas? Yes?
Isn't that equal to?
You have to speak real loud over the noise.
Isn't that equal to the natural log of AB minus the natural log of?
Absolutely. Okay. Good first step, thank you. What else can I do to break this down? Yes, John? Okay, ln of A plus ln of B minus ln of cube root of C. Not quite done here. Maybe this will help. I rewrite this as ln of C to the 1/3. Yes?
So you would make that third term 1/3 times LNC.
Absolutely. All right, I can always move this, the exponent here, either in front or I can move it back if I want to go the other way. Okay, all right. Hope you're warmed up. We want to look at something new now. There's a certain kind of problem that it's going to take a little work. Problem is, let's say I have something like this, log to the base 8 or 5. And what I want to do is, I want to convert that to some other, maybe more convenient base, like say 10. I want to know what that value is, right? So this is just some number, but I'm expressing it as a log to the base 8. I want to know if I express that number log to the base 10, what is it? That's the chore. So how do we figure out how to do that? Well, This is the trickiest thing we've done with logs. It's probably the trickiest thing we will do with logs. So, but it's not that tricky. It's pretty straightforward. So we're going to start with the expression log to the base a of x equals p. So a is my base, x is the value of the function, and p is the exponent for log. And I want to rewrite this using the inverse function, right? That means I want to write a to the p equals x. Okay. Now you should kind of start to feel comfortable with this switching. It's the same statement, it's just using, instead of the inverse function, instead of using the function, in this case the log, the inverse function, log a to the x. Okay, so now we take this expression and we find the log, but to some new base. We call it b, for both sides. And I want to drag this exponent over here. Okay. And at this point, I look at this and I see, well, I've got a, b, x, p. I have a lot of variables here. I'd like to simplify it a little. And I'm going to simplify by simple substitution here. In particular, I'm going to go back to my original expression. I have p defined here as log to the base a of x. So I'm just going to insert that. Log to the base a of x. Log to the base b of a equals log to the base b of x. Well, here I have one version of my change of base formula. I have some number, right, which is log to the base b of x, and I'm expressing that as log to a different base using that same value, and I see that what I need to do is multiply by a constant. So if you think of this here as log to the base b of x, what have I found? It's log to the base 10 of x times, I guess I want to put this on the other side. Log to the base 10 of 8, which of course I could pull up here if I wanted to do that. So that's what log to the base 8 of 5 is equal to in terms of some function log to the base 10. Okay. Oh, that would be my 5. 5 raised to the power of log to the base 10. Okay, we don't usually use it this way, but you will see it this way a lot, or you might see it as log to the base a of x is log to the base b of x over log to the base b of a. And this is a fairly easy way to remember it, because at least you have the same base here, log to the base b of x over the log to the base b of a. Okay, again, this is a change of base formula. Right. Let's see what that would be good for, practically speaking. If you look at your calculators, any of you who have a scientific calculator, you'll notice there's no log to the base 8 button. Right? We have a log to the base 10 button, and we have a log to the base E button. So if we wanted to know what this is equal to, we're going to have to do something. Right? We're going to have to change the base. So according to our formula, this is log to the base 10 of 5 divided by log to the base 10 of 8. And we do have a button for log to the base 10, right? So we can plug this in, and what do we get? We get about 0.77398. Okay, that kind of makes sense. 5 is between 8 and 1, so we'd expect the log to be between, yes?
I have just one question. Usually when I use log, I always write natural logarithm instead of natural logarithm of 10. I always use ln instead of log. Would that be right in an exam, or would you mark it as right? Or
Yeah,
do we have to write
good question.
Because
Were you here?
yeah,
Wednesday?
I was here the other
Okay,
time. But I can't
that's fine.
remember what you said.
I don't mind repeating myself. So,
I mean, I know the difference between both, but like I just
yes, I'm going to
use.
disambiguate.
Okay, for sure.
It's a nice vocabulary word. Disambiguate. So, if I write log to the base 10 of something, that's unambiguous, right? It's very clear. If I write ln of something, that way, that should be clear. This is just equivalent to log to the base e of something. The notation that's ambiguous is this, log. Say it's log of x. The problem with log of x is, if you're in a science class, what they mean is log to the base 10. If you're in an upper level math class, what they mean is log to the base e, because higher level mathematicians don't care about log to the base 10. That's just how many figures we have, right? In math classes like this, or calculus, depends on the book, depends on the professor. So my recommendation is never write that. Always write either this, this, or this. That's how I try to deal with
Yeah,
it.
that's what I
Could-
usually do too.
Yeah, okay.
Yeah, I was wondering like if I could use ln.
Yeah,
instead of-
absolutely. ln is unambiguous. If you look on your calculator, it's probably gonna mean
yeah, I have
this.
log 10 and natural log, so I always usually use natural log.
Yeah, this is a notational issue, and it stems from the fact that from a scientist's point of view, a log to the base 10 is more important, but from a mathematician's viewpoint, log to the base e is more important. So again, you know, you might have to be, in the future, you might have to be aware of the context of the C log. And sometimes, there is one exception, which is sometimes log, it's unimportant what the base is. And then you can just write log, and you know, in other words, if I said, you know, log of x equals log of 3, it doesn't matter what the base is. Okay, change of base formula. Any questions? A little tricky, you know, try and learn it as you do the homework. Either memorize it or remember the steps I used that I erased on how you get it. Okay. We're on to the next section, which is, now that we know about exponential functions and log functions, we're going to look at exponential and log equations. That is, equations that have a log function or an exponential function that we have to deal with. First thing I want to say that the book makes a big deal out of the fact that both the exponential and the log functions are one-to-one. The importance of that in the book is that if you see something like this, a to the x equals a to the y, since these are one-to-one functions, you can conclude that x must equal y. Similarly, if you have log to some base, a of x equals log to the same base of y, you can conclude that x equals y. There's a property of one-to-one functions. I think that's kind of an unimportant detail, and I'll show you why. It's nice if you want to see things in terms of properties of functions, but there's a straightforward way to avoid that step. If I were to have a to the x equals a to the y, well, I can certainly do the same thing to both sides of the equation. I can apply each of these to the function that I want. In this case, log to the base a, ax. That's going to be equal to log to the base a of ay. Judiciously chosen base here, you'll see. And my exponents now can come out in front. So I have x times log to the base a of a equals y times log to the base a of a. At this point, it's a simple matter. This is a constant, so I can divide it out. But I can do something even simpler. I can evaluate it. Well, what is the log to the base a of a? In other words, a to the x equals a. That's writing it as an inverse. What is the x?
1.
It's 1. Yes. Something you need to know, right? Okay. Still kind of disturbed about my keys, but all right. Let's talk about what I'm doing here. Well, one way of looking at it is I'm applying the inverse function. In other words, I have some function f of x, and I apply this to the inverse function. What do I, of course, get? Really important. Yes, I just get x. Let's think about that for a second in a different context. If I have a simple equation, 2x plus 3 equals 7, and I want to solve this, how do I go about that? Well, of course, everyone knows I'm going to subtract 3 from both sides. But what's that about? Well, adding 3 and subtracting 3 are inverses. Subtraction is an inverse. So, okay, I get 2x equals 4, and now I divide by 2. Why do I do that? Well, dividing by 2 is the inverse of multiplying by 2. So that's how we unravel this, and we get x equals 2. We're going to be doing the same thing with logs and exponential functions, using the fact that we know one is the inverse of the other to solve an equation. Okay, we're going to do this. But we're going to take kind of baby steps. So let's take a look at a very simple equation. 5 to the x equals 125. Okay, there's two approaches to this. One thing I could do is I could say, well, 5 to the x equals 125. I know that that happens to be 5 cubed. And that tells me that x equals 3. That's one approach. Another approach is I could take both sides of the equation, find the log to the base 5. Okay, my x can come out in front here. And again, log to the base 5 of 5 is 1. So it was a good choice of the base. And now I know my x is log to the base 5 of 5. Well, I already have a value there, right? I might at this point, wake up and recognize this is log to the base 5 of 5 cubed, right? So this is just 3 times, again, 1. Or I might have to, if the numbers aren't so nice, I might have to resort to that change of log function, right? This is log to the base 10 of 125 over log to the base 10 of 5. And then I can punch this into my calculator. And of course, I would find out the answer was 3. Right, so far we're okay? Let's look at something a little more complicated. Let's take a look at 5 to the 2x equals 5 to the x plus 1. So again, I have a choice. I could recognize that because this is these are one-to-one functions raising to a power, I could just immediately set 2x equal to x plus 1, or I could find the log to the base 5 of 5 to the 2x on both sides. I'm emphasizing this long way around because there are going to be problems where you're not going to have a nice route here. 2x log to the base 5 of 5 equals, oh, I repeated myself here, x plus 1, x plus 1 log to the base 5 of 5. These are both 1. So I just have a nice, simple algebraic problem, and I get x equals 1. In this case, there's no issue, but it's a good idea with these kinds of problems to check them by plugging your number back in to the original equation. You want to make sure it's going to work. In this case, 5 to the 2 times 1, that's 2, equals 5 to the 1 plus 1 is 2. No problem. It is possible to find that in some instances a value you compute out will not actually work. We'll see that today. Okay. Let's go one step more complicated here. Let's look at this expression, this equation. 3 to the x plus 2 equals 7. Okay. So here I can't just use this one-to-oneness so easily. This is not a power of 3. But I can still find my log to the base 3 of both sides. And again, I can move my exponent out front, so I get x plus 2 times log to the base 3 of 3 equals log to the base 3 of 7. And of course, this is 1, so I just have x plus 2 equals log to the base 3 of 7. And at this point, as long as you recognize this is a number, it's just a constant, this is just a simple algebraic problem now. I subtract 2 from both sides, and I get the answer log to the base 3 of 7 minus 2, which, if I want an approximate number, or some decimal expansion, I'm going to have to convert this using my change of base formula, so my calculator can handle it. And I'll get some, what do I get here if I do that? Negative .22, we'll just say 9. It's just an approximate value that would make this true. When you actually do these, you're either going to find them pleasant, tricky puzzles that you'll enjoy, or you will find them maddening. But the only way to be able to learn how to do them is to practice them yourself. So I encourage you to do the homework on these. I'm going to move up the chain here in complication. We'll introduce an equation with E. E is just a funny number, but it's just a number. Shouldn't let it throw you. We're just going to treat it like any other number. What would be a good first step here to solving this? nothing fancy. Just want to unravel this and get to my x. So that's the first thing I would want to do. Yes, here. Absolutely. Something we all learned in Algebra 1, right? Nothing fancy. So I get e to the 2x equals, what's that, 5/2. Okay. All right. Now I have to be a little smarter. I'm raising e to the 2x. I'm raising something to the power of e. Well, what inverse function would I want to apply to get myself into the next step?
Natural log.
Natural log, yeah. Natural log, or the log to the base e. This we're very fortunate you do have a button on your calculator, right? If we ever need it. Okay, move my exponent out here. The natural log of e is, of course, 1. So we just have 2x equals the log of 5/2, and finally x equals the log of 5/2 divided by 2. Okay. Question?
No.
Nope. Okay. All right. Let's keep going. These just get harder and harder. Very slowly. Take a look at e to 3 minus 2x equals 4. And what would my first step be here? Aha! I just thought of some place I could have lost my keys. Ponder this question.
Yeah, that's what I
What did we come up with?
I know 4.
What are you going to do with this? Take the natural log. Both sides. Okay. Move my exponent over. I make a log of E1. And finally, I just have to solve for x here, right? Minus 2x equals log of 4 minus 3. And x equals, dividing by minus 2, 3 minus log of 4 over 2. But let's just plug this in to make sure this seems to work. right? We had e to the 3 minus 2 times our answer has to equal 4. So our answer is 3 minus log of 4 over 2. All that 2 cancels. 3 minus 3 cancels, minus a minus. This is e to the log, natural log of 4 equals 4. Well, that's just very clearly true, right? That's just saying the inverse of the function equals x, right? In this case, x is 4, right? My log function of 4, and then I plug that into my inverse, which is e raised to that. It's got to be 4. Okay, let's do something hard. At least harder than we've seen so far. Now, I kind of like this problem because even though you've never seen anything like it, maybe, you've seen all the moving parts. E to the minus 2x minus e to the x minus 6 equals 0. So before we get going on it, let's be careful. Finding the log of both sides here is going to be completely useless. Let's think about why. I mean, we don't really, like if you saw this, you might foolishly think there's some law of logs here, but there isn't, right? We don't know anything particular about the log of a plus b, log of a minus b. We know something about the log of a times b. You can split that up, but this is not something of any value unless we actually have the numbers and we can add them. So that's one problem. What's the log of 0? Anyone remember? Okay. Think about what the log function looks like. Remember, the exponential function looks like this. The log function is its reflection. Right? So this is log of x for some base. What's the domain of the log of x? What are the x values I can plug in? I mean, another way to ask that is, what's the range of, we'll just call this e to the x, right? What's the range of an exponential function? What values can I get out of an exponential function? Thank you, John. No? Need to know this. Yes?
Greater than 0?
Yeah, these are greater than 0. The range is greater than 0. So the domain of the log is x greater than 0. While we're at it, what's the range? What's the range of the log function? Should be able to look at this graph here, right? Right? When I ask about the range, I'm asking about the y values. So which y values do we go through here?
All all reals?
All of them, yes. Yeah, the range is all real numbers. Again, just switch it around for the exponential. The domain is all real numbers. Okay, so log of 0 is undefined. It's not even in the domain. So that's not going to help. What we need to do this problem is remember something we've done before in an easier context. The thing to realize is e to the x, e to the 2x is e to the x squared. So we have something squared minus that same thing minus a constant 0. When you see that, even if it's looks funny like this, you should think maybe this is a disguised quadratic. Quadratic. Okay, what do I mean by that? Well, if I do a substitution here, if I say y equals e to the x, then this becomes y squared minus y minus 6 equals 0. Well, I think I can find y, right? How am I going to do that? I'm going to find y here. Yes?
You factor it out.
This is an easy factor. I mean, if I can't factor it, I could use quadratic formula, but, all right, y, looks like 2 and 3, and where's the plus go, and where's the minus go? The minus goes here, right? Plus goes here. So I know y is equal to minus 2 or 3, okay? But I don't really want to know y, I want to know x, right? So I have to look further. So I get either e to the x equals 3, or e to the x equals minus 2. I know how to solve those, right? You find the natural log of both sides. You get x equals natural log of 3, and x equals the natural log of minus 2. But there's still a problem. What's the problem here? If you're unsure, plug this into your calculator. Yes?
It's undefined.
It's undefined, yes. And if you plug it into your calculator will tell you. You can't find the log of a negative number, you can't find the log of 0. So this is kind of a phantom solution. You could even plug it back in. You could plug in you could say e to the 2 times the log of negative 2 squared minus e to the log of negative 2 minus 6. And you might do something screwball here. You might go, oh, well, that's 2 log of minus 2 squared minus log minus, oh, I'm sorry. This is minus 2 squared minus 2 minus 6. And you get 4 plus 2 minus 6 equals 0. You can fool yourself. But this is undefined, so you can't really do that. Yes?
Aren't you able to pass under like main equation, under like first, not like the top one, but like yeah, this one. And should I put the minus e x minus 6 on the right side and like do a like
Well,
ln of like both sides?
so you want to say e to the x times e to the x minus 1 equals 6. I think that's what you want to do.
Yeah, we can do that too. But like, I wanted to like give.
You're going to have to come up and show me because I'm not going to get it. Okay, yeah. Yes, you can do that, yes. You get 2 over here, that's nice.
I can't remember, but I'm pretty sure it's.
Yeah, see, the problem is this. Remember what I was saying about log of a plus b? We can't really do anything with that. I mean, the only thing you could do with this is you could raise this to e.
Yeah.
And then you get e to the x plus 6, and you get this back, the same thing we started with. Yeah. It's a good try, though. Yeah. Now you see why you gotta recognize this guy is quadratic, basically. All right. I think we run out of steam for today. I want to say a couple things about the midterm coming up. Right now, it's right now. It's a week from Monday. It's going to could cover anything that we did in the class at the beginning, but mostly it'll be things from where we left off, the last midterm, to exponential and logarithmic functions and equations. We're going to start working on some trig next week, but that will not be on the exam. That will be on the final. Okay. All right. Anybody who has...
Yeah.
I might have left these back in my office. It's hanging.
It's probably